Good morning, everybody. My name is Eber Barbero, and today I want to talk about fatigue. This is video number 2 on fatigue, and video number 1 it has an introduction to the physics and phenomenology of fatigue. Video number 2 we introduce the stress life method, and it's going to take us several videos to complete the discussion about stress life. And in this first video, we'll introduce the main aspects of it. And so with that, we can get started. All right, so first a review from the previous video. All right, we learned that stress concentrations are one of the likely initiators of fatigue. And also material defects such as voids, dislocation, segregation can initiate fatigue also. And even if no defect is detected, yet you cannot see it, fatigue can take hold if the number of cycles and the stress are large enough. Characteristics of fatigue are that usually it takes many cycles, and by many we mean hundreds, thousands, hundreds of thousands of cycles to produce a crack that is sufficiently large to fail the specimen. The bad things about fatigue are that the crack propagates undetected without warning. Otherwise, you can take the part or the component out of service. And the other bad part about fatigue is that the final failure is brittle. And brittle failure is bad because you have total collapse. All right, it's not deformation, lack of function. So now in this video, we start to work on how to predict fatigue failure so that we can design against it. All right, so there are 3 methods available for fatigue analysis and design: the stress life method, the strain life method. Okay, we have stress, we have strain, and then we have fracture mechanics method. We're going to work in this class with the stress life because it's the easiest to apply. Most important, it requires least amount of data, and the data is easier to find or even estimate. Unfortunately, it's the least accurate, but the accuracy enough that makes it, even though it's the least accurate, is the most popular. All right. A strain life method is similar to stress life. So if you learn a stress life, then if you have to use a strain life, you can pick it up yourself. The data is more scarce, so that's why we don't use it. It's more accurate than stress life, but not so much, and definitely less than fracture mechanics method. Fracture mechanics method, you know, I love fracture mechanics, so it's a very good method, but it's the hardest to use. The data is most scarce, but it's the most accurate. So that's for high-end work. So we will use a stress life method. Because it's very popular. Even some FEA codes implement a stress life and sometimes a strain life equation, and both are similar, so you can use it. Okay. So as I mentioned, you know, fatigue is a purely empirical topic. So you start with the data. All right. So you need data. Okay. The best is you get your own data, or you pay somebody to get the data for you. That way you're sure that what you have applies to exactly the same material with the processing conditions that you have. Then if you don't do that, then there is always uncertainty, and you're going to have to cover that uncertainty with additional safety factors, which is going to make the parts and the components heavier and less efficient. All right. So like everything, if you want a lightweight, you have to pay the price. So to do testing, somebody else has done, or you decide to do it. Most people use the R.R. Moore specimen. Yes, this is this specimen here. And so we describe this specimen here in detail so that you understand the limitation of the data, because then we're going to have to correct that data for a practical application. So in this specimen, you know, it has this funny shape to make sure that we have a section that it has a smaller cross section. A smaller cross section means a smaller second moment of area. That means largest stress, sigma MC over I in bending. And so that way we know that always the specimen will fail here. It's not going to fail here where it's thicker, right? It's a circular specimen like a shaft with end shaft like this. This is a cross section when I look from this side. If I look from this side, that's what I see. And this is mounted in this configuration, which is called 4-point bending, because there is 1, 2, 3, 4 points. All right, 4-point bending produce a constant bending moment in this region and zero shear in this region. I encourage all of you to go and do the shear and bending moment diagrams. I know that you're sick of doing shear and bending moment diagrams in my class, but you should do it because practice makes perfect. Have you heard that? Practice makes perfect. So you will see there that the shear force is equal to P in this region, because this P cancels this P, so the shear is 0 here, and then minus P over here. Okay, and the bending moment is P times D, or P times D here, and it's present here. So why R.R. Moore did this? Because then he put the specimen in a situation where he knows where he's going to break, and he put only bending moment, no shear force, to reduce the number of variables. In experimental methods, you want to reduce the number of variables. You want to isolate the variables. So you study the effect, in this case, the effect of bending on fatigue strength, and it's not contaminated by some shear, because otherwise you have to say how much shear. Well, 10% of bending, 20% of bending. Try to avoid that. So this is pure bending. I don't have to worry about shear. Shear comes later, and we'll figure out what to do. So pure bending moment in this region, a smaller cross section, so it's going to fail there. Now in the textbook, if you look at this figure in the textbook, you're not going to find this little crack. I put this little crack because I believe, like I demonstrated in the previous video, that the fatigue failure is due eventually to a crack. And for this crack to occur, okay, the dislocation has to coalesce to make the crack to begin with. And where are the dislocation going to come from? They're going to come from a defect, okay? Could be, you know, a little stress concentration, a tool mark that was left there. Could be an internal material little defect due to segregation, whatever. So in order to represent it, I just go there and draw a little crack, which is not going to be that big, but you have to see it, so I put it there. And okay, so once I have this drawn and this loaded with this load P, okay, with this load P, we can control this load P in the machine to put whatever P we want, so that we get whatever stress we want here. And we will put stress as low as 0 and as high as the tensile strength of the material, SUT, all right? And so then after I do that, then I turn on a switch and this starts rotating. There is a motor that makes it rotate. And it will rotate like this. So at the beginning, point A, my defect, is here, down here. And since the bending moment is positive, this is tensile stress, so the crack opens. And if I plot sigma here, sigma I calculate like the moment, which is P times D multiplied by the radius of this divided by moment of area. That's it, MC over I. So I calculate sigma and I put it there. After this start rotating, the stress is going to go down because this point is going to go behind over there until 0 there. And then it's going to go negative there. So it's going to go like this, 0, and then negative. And then it's going to go back to 0 when this point goes here, right there is 0. And then it's going to go positive to this point, and that completes one revolution. So that is n equal to 1. So in one revolution, the point, material point, this one that I marked, experience all the stresses from positive to negative, again to positive, although this point belongs to n equal to 2, that because I'm starting cycle 2 right there, okay? Okay, so, and the type of loading, this particular type of loading is called alternating, all right? This is not fluctuating. I will explain fluctuating later. Alternating means that the stress is plus minus. So this is a value and this is minus the same value. And if you look at this plot, we can say also that alternate has 0 mean, because if you integrate this from 0 to 2 pi, this area plus this area is cancelled by this area. So the average stress is 0. It's like if it is not loaded statically. But dynamically, is loaded this way, and we call this alternating. And of course, it's repetitive because next revolution is going to do this, and next revolution is going to do that, and so on and so forth. All right. Okay. So another note is that important is that the specimen is carefully machined and polished. Okay. So this thing that is carefully machined and polished means that it eliminates the effects of surface imperfections, because we guess that if we have tool marks that are very deep, those are like almost like cracks, and if it's polished, there are no tool marks, so the specimen is going to last longer. So R.R. Moore made it into a polished specimen to eliminate all the other effects and concentrate only on what the material can do. Okay, so then once we have the specimen and how it's loaded, then we move forward and we see the data. So okay, here we can see the data. The data are all these dots, all right? These dots. And the data can be fitted with 3 lines. Okay, there is this line with the slope C, which represents, well, these points in the low cycle fatigue. Low cycle fatigue ends at NT, which in this case is, say, this is 1, 10, 100, this is 200. So right there is 200. But this number depends on what data you get, okay? In the literature, or at least in the old days, they like to say, assume that NT is 10 to the 3, but you can see it's not true because 200 is far from 10 to the 3. However, when you had to go and you didn't have a calculator, but you have only a slide rule to do the calculation, then you want to assume as much as possible to make the calculation easier. We have powerful graphical calculators, so we don't need to do that. We can use a real number. If the data says that NT is 200, okay, NT is 200. Okay, but you will see in many places that they assume right off the bat that NT is 10 to the 3, all right? Now, this point, how do you find this point? You find this point visually where these 2 lines intersect. So you put a line that fits well the data over here, and then you put another line that fits the data very nicely there with a correlation coefficient as low as possible. And you can do that in Excel. And when they intersect, you say, aha, I have N sub T. There you go, okay? So this is low cycle fatigue. Now the plot is base log 10 log log. That means both axes are log 10. So this axis is log 10 and this axis is also log 10, all right? Now don't be fooled by the label. Yes, you will see in all the textbooks, it was going to say number of cycles n. But if you actually want to do this plot, you got to take the log of n to put it in there. Or if you do say in Excel, you put values of n, life, and then you check a box somewhere that says, give me a log scale. Yeah, but that's what the computer is taking the log for you. So either you take the log or the computer take the log, but somebody is taking the log, all right? And so that means that this is log n, not really n like it says there. And we need to understand this in order to derive the equations. Otherwise, you cannot derive the equation. Same thing here. Here it says fatigue strength, SF, but really we put log of SF, yes? Another consideration is that although it says fatigue strength, why it says fatigue strength? Because the points are all failures, yes? So when the stress reaches the value at which it fails, we call it strength. But we can use this plot entering through from here with the stress. I will explain to you in a minute. So even though it says fatigue strength, we can enter here with the stress. We'll see about that. Anyway, it's log, okay? All right, and low cycle, it has a slope C. Yes, we've seen that. It's slope C, and it goes from 1 to NT, the life. So from 1, 10 to the 0, to NT, which is 200 in this for this particular data, okay? Then there is another line that fits nicely these points, and this is what we call high cycle fatigue. Okay, here I put the finite life, but it should say high life. And this is a slope B. Yes, it has a slope B. And then N is between NT and NE. Yes, between NT and NE, which in this case is 10 to the 6. And this is what most of the literature assumes, but it's not true all the time. It could be 10 to the 7. It depends on the data, all right? Okay, so then we have this line that fits very nice the points, and it has a slope B and intersects there. All right, so now let's talk about this intersection. Once we find this intersection, there is a value of strength, SF, for this intersection. In our case, is 100, yes? Now, we could name this something, but in the literature they don't give it a name. What they say is that this value is F multiplied by the SUT. The SUT is a value that is available in the literature because it's the tensile strength. So every material you can find the tensile strength. So basically what they say is, okay, at which point in strength does these two lines intersect? Okay, they intersect when the SUT is reduced by this factor F, okay? And so this is like a knockdown factor. It's a value that reduces SUT to come to this point. So how do we calculate SUT? Well, if we have the data, that means we have these points, and we know this. Okay, this is FSUT, which in our case is 100, and SUT looks like it is 100, 110, 120, 125. Let's say it's 125, yes? Okay, so it's 125. And so if F multiplied by 125 is equal to 100, that means that F is 100 divided by 125. And 100 divided by 125 is 100 divided by 125, 0.8. So yes, the factor F is 0.8, and this is very common. In fact, if you don't have data, it's a first approximation for a back of the envelope calculation. You can assume F 0.8, and it's a good approximation. And F could be 0.9, it depends on the material, okay? But it's a good approximation. We will derive an equation to calculate the F exactly, okay, from the data. All right, so we got there, and we got these, okay? Now, remember, how do I make these points? To make these points, I start at 10 to the 0, that is one cycle, so I'm gonna do this once in the machine. And I want the specimen to break. So if I want this specimen to break, the amount of stress that I dial up in the machine is SUT. And since I know the material breaks at SUT, as soon as this specimen does this, boom, it breaks. Okay, so I'm gonna get this point. Now, no point putting more stress because it's gonna break. So we put less stress. Okay, let's say we put, I don't know, 110. We put 110, and then we go here, and it breaks there. And if we put less, 100, it breaks there. And okay, and that gives me this line. And then if I put 90, well, I don't have a point for 90. If I put 80, okay, yeah, I have points for 80, it breaks there. Let's say 70, yes, I have 70. 60, do I have 60? Yes, 60, I have there. 50, yes, I got points for 50. So I got all these points, and I make this line. Okay, with correlation coefficient as low as possible. I do that with Excel, no problem. All right. So, but the thing is this, now if I keep lowering the stress, and these are all different specimens, so you can imagine this takes time and it takes money because you have to make many specimens. So now I got to 50 and I say, oh, I'm going to put 40. Okay, I put 40 and nothing happens. And you can see that even at 49, which will be these points, or 48, I don't know, we have what is called run out. These arrows are run outs. Run outs means that I got tired of waiting. Because 10 to the 6 is 1,000,000 cycles, 10 to the 7 is 10 million cycles. This may take a week. And after a week, I need the machine to do something else. So I say, stop it. And so I label it like that. Once I get many runouts, then I'm convinced that this number is what I call endurance. And I label the strength S sub E. It should be here, it's 50. So my S sub E is 50. And this is the endurance limit, which I have right here, endurance limit. Okay, and that is when n is greater than n sub e, which is the life at endurance, at the beginning of endurance, this is infinite life. Okay, so then this is constant, and if I put in the actual application, if I put anything less than 50, the life will be infinite. All right, so if I design for infinite life, the maximum I can put is this value of S sub E. All right. So we got that. Okay, so basically we have the diagram. we have the data on the diagram, and we identify the regions, and we identify the parameters. Oh, one parameter I didn't talk about it is about the intersection of the high cycle fatigue life, which is this, with this axis. And I say here sigma f prime equal to A. When we have a specimen, not an actual component, these two numbers are the same. But when we have a specimen and a component, these two numbers are different. And to differentiate, I had to use two different values, two different letters. And this one I call a sigma f prime from the literature because it has a physical meaning. And then for a specimen, this will be the value. And for component, this number is going to change, all right? And I will explain that later. Okay, so we got all the parameters from the diagram. And so we can move forward and try to find equations to represent this diagram. Now, why do we want equations to represent this diagram? Before we do that, before we work on the equation, let me explain how do we use this diagram. Oh, yes, this is better. Okay, how do we use this diagram? We can use this diagram for design in blue or for analysis that will be in red, this. So, okay, so for design, if we have this diagram on paper, in log paper, which in the old days you could get a log paper, put the data on paper, and then measure with a ruler on paper. I've done that when I was young, but we don't do that anymore. We use a calculator or MATLAB. Okay, so in design, how do we use this diagram for design? Okay, let's say your boss comes and says, I want you to design this component for a lawnmower. Maybe let's say this thing that you pull the lawnmower to start it, and he says, I want this to last 100,000, which is too much for a lawnmower because 100,000, 10 to the 5, you start the lawnmower 100,000 times. I don't think so. It's going to break before that. But okay, let's say he wants 100,000 for that component. Okay, so then what do? You say, okay, you want 100,000, so I'm going to go enter here, 100,000. I'm going to go up to the diagram, then I'm going to go left, and I'm going to read the strength S sub f. That means that the strength, which is 50, 60, is 60. In this case, is 60. So that's the strength that I can use in the design. All right. If the load is quasi-static, I can use SUT with a safety factor, right? And SUT is 125. But if my boss wants 100,000 times this to last 100,000, then the strength I can use in the design is only 60, which is less than half of SUT. Your part is going to be more than double in weight because you want this part to last so long, all right? And of course, if you are not so stringent and you say, oh, I can tolerate 10 to the 4, then of course you get more strength. That's the way you use this plot for design. Now for analysis, okay, let's say that the company you work with just acquired another company that makes lawnmowers. And you got this product, but you have no documentation. So you don't know how much things are going to last. So your boss comes and says, okay, we got this lawnmower. And so I want you, for this particular component of the lawnmower, I want you to tell me how long it's going to last. And you say, oh, okay, so what do? I go and analyze that component that is already designed and built. So I measure it and then I analyze it. Analyze it, which means if it is in bending, it's MC over I at the critical point. You remember I told you how to find the critical point. Most often is the point that has maximum bending moment, but the shear could get involved, right? So you go find the place that has the most stress, and that is the maximum stress. So then you come and you enter with that stress. So you entered here. All right, you see, I told you that you could enter with the stress. So if you have the part already designed and maybe even built, you calculate the maximum possible stress and you enter the diagram on this side. And then you go to the line and then you go down and then you find, okay, this part is going to last 10 to the 3. That's only 1,000. So it's not very good, but maybe your boss says, sell it anyway, and then we figure out what to do when people complain. But anyway, that's the way it works. There is analysis. You go with the stress that you have to calculate, and then you determine how much is going to last. or there is a requirement for life, and then you determine what strength you have to use in the design to meet this requirement. So you see, it's very practical. This is really, really practical. Okay, so now we go back to what I wanted to do before, which is to substitute this diagram, yes, by equations, because I'm not going to go buy log paper. I don't know even if it's possible to buy log paper, and I'm not going to measure with a ruler. I don't have a ruler. Okay, I have my lab. Okay, so let's go and see if we can derive this equation. Now, to derive these equations, it's going to be kind of like not complicated, but tedious. Okay, so you have to bear with me because the reward is worth it. Okay. So we're going to start with high cycle fatigue, okay? So high cycle fatigue range from NT to NE. Yes, it's from NT to NE. It's in this range. I start with that, okay? Because this is the easiest way to derive the equations. All right, now if I had to write an equation for this black line over here, remember this axis is log n, not n, and this axis is log SF, not SF. Otherwise, you cannot derive the equation. All right, and I know the final equation, so I'm sure. Okay, so the equation for a line, everybody knows, right, is y equal to m plus a constant times x, which x will be this. So, okay, what is y? Oh, y is log SF. Log SF is this SF, but log is this. And the line starts at the intercept. This is called the intercept on this axis, which technically is called the ordinate. Yes, and this is the abscissa. Okay, so at the intercept is A, or for the specimen sigma f prime, but let's just use A. Okay, so, okay, we got A, log A plus B, but B is going to have to be negative because this is going down. Okay, fine, B is going to be negative. Log N, because the axis here X is log N, all right? Everybody good with this? Okay, so now you gotta use two of the properties, the two fundamental properties of the logs, okay? One is that you can put this B on top here and write it there. And the other is once you do that, you have log A plus another log. You can add them by putting the A as a multiplication here as a product. So this is the same as this. Review your logs because we're gonna do a lot of logs. So we have this equation. Now, once we have this equation, then what we can do is we can take the inverse log. What is the inverse log? The inverse log is 10 to the x because it's this base 10 log. So you do 10 to the x of these, you get SF. You do 10 to the x of these, you get A, n to the B. And this is the fundamental fatigue strength design, strength equation. Yes, it's the only equation, well, not the only equation you have to remember, but the most important equation you have to remember. All right? Now, this equation, when you look at it this way, okay, it's a power law. And a power law is a very important equation because it fits very well a lot of physical phenomena, a lot, okay? And so it's good to know how to do things with power law. Power law has two parameters, A and B, which we can get from data, all right? Or from estimated values. Okay, so you see at one point in the next video that we will say, hey, look, the best is to have data, but if I don't have data, okay, I can estimate. Once you estimate, you will need the equations in order to get A and B so that you can use that equation. Now, question, is this a design equation or an analysis equation? Okay, well, the independent variable is the n. Yes, and the dependent variable is SF because you enter with n and you calculate SF. What did I tell you before? If you enter with n, it's because your boss wants 10 to the 5. And then you get a strength here, which is 60, which is your design strength. If you design the part with that value plus safety factor, of course, then the part is likely to take this 10 to the 5. I never say sure, but it's likely, okay? To take this number, all right? So it's a design equation. This is a design equation. All right, what if you need the analysis equation, which is the red? Like I know the part, I can calculate the stress because I know the dimensions and the load. And then I want to know how long it's going to last. Okay, you go this way and you go this way. Well, you got to invert this equation. And how do you invert this equation? Put the A below the SF. Here's the A below the, oops, I changed SF for sigma F. Yes, because when you enter this way, you don't enter with a strength. You enter here with sigma f, which you calculate as MC over I or whatever, P over A, whatever, it could be a tau, all right? You enter with sigma, you don't enter with S. So I switch the S by sigma, okay? This I'm doing. You won't find this in the textbook, okay? But I'm doing it because that's the way it is, really. You don't enter with an S, you enter with a sigma. So this S, when I invert, it becomes a sigma. I'm sorry, it becomes a sigma. So sigma F, F is for fatigue, okay? So divided by A, because A comes down here, now I have to power to the 1 over B to delete this B, and so 1 over B, and I have this. This is the analysis equation, okay? So the analysis equation. But you don't need to remember this equation because you remember that one, you know how to invert, okay? But still, we have to find the parameters A and B. All right, this is high cycle fatigue. Now let's talk about low cycle fatigue for a minute, all right? So for low cycle fatigue, we do the same, okay? We got a line, all right? An advantage is that while for high cycle fatigue, we don't know yet A, for low cycle, we know this guy, SUT is known. Okay, so this is a line that starts at SUT. So log SF, this is log SUT, yes, the ordinate at the origin. This is the ordinate. This is called the ordinate at the origin or intercept. And is log SUT. And plus C, well, C be very negative because it got to go down, is negative. And then log N, that's it, that's the equation. Then we do the same magic as before, take 10x, and we get the design equation, and this is the design equation. SF, SUT, to the C. It looks exactly like the previous one. All right, the only thing is that now we have C instead of B, because that's the slope. And then the A is no longer there because SUT, because we know what SUT is. We can get it in any handbook for any material, and it gives us this. And if you wanted the analysis equation, well, you know what to do, right? You don't, right? You replace sigma F by SF by sigma F, divide by SUT, okay, and then to the 1 over C, and that gives you N, and that's the analysis equation. So you don't have to remember that. Okay, so we got the basics of high cycle and low cycle equations, but not everything yet. Okay, we need to work some more. All right, so let's see. Oh, okay, no, so now we work some more. All right, so in this slide, we're gonna divide this equation for the slope C. Okay, the caveat is that it's in terms of NT, which we can, either we know from the data, because we just look at it and we say, oh yeah, it's 200, or if we don't have the data, we can assume it's 10 to the 3 because many people do that, and all right, it's not so exact, but what can you do? If you don't have the data, you don't have the data, you gotta move forward. But the problem is that you need the F, and the F, how am I gonna get the F? Well, I said already that if you're desperate, you can, desperate, I mean, you don't have data, you're in a rush, you gotta get a number, okay, preliminary design, then put F.8 and you move forward, all right? And if you do that, then okay, you can get the C immediately, all right? But I want, all right, then that's it, that's the end of it. But I want to show you how you get this, okay? Because we're gonna have to do a lot of these derivations, so it's better to start with this one, which is not difficult. So, okay, this is the equation, SF, SUT, N to the C is the equation for this line, all right? It's a power law, but in log is a line, which is great because if the data fits a line, then you can get the slope and the ordinate with Excel. In this case, you know the ordinate, but in this case, no. In this case, you get the slope B and the ordinate with Excel or some other program, MATLAB, whatever. And because in log is a line, right? But in reality, it's a power law, it's this. All right, so what do we do to get the value of C? Or evaluate at n equal to nt. So it becomes SF of nt. This is not multiplied by nt. This means evaluated at the value nt. And okay, evaluated at nt, that means SUT, N, C, and this N, I put NT, this T there, because I'm evaluating right there. Okay, so then, of course, now I define F in such a way that SFNT is FSUT. I told you that already. And now we set these two sides equal. So we say SUT n to the CT equal to F SUT, yes, from here. All right, so from here F is equal to, because I cancel this with this, so F is equal to NTC. And all right, next, take a log. And sometimes these things are not obvious that you have to do. But okay, take a log, fine. Take a log F equal to C log NT. Well, why the C is here? Because when you take the log of this, you can bring the C out of the log this way. This is rule number 2 for the logs. And from here, oh, get the C. C is log F divided log NT. And I got this equation. If I assume NT is 10 to the 3 and F is 0.8, that, boom, gives me a slope, which may not be real or not exact, but at least I have C, I can move forward, all right? So I can move forward without data. Okay, that's the trick. Okay, so obviously we're not done. We're not, but the video becomes very long and I'm tired, so I cut it here and continue on video number 3. But before I move on, I want to say a few things. I put word of caution because I want you to get prepared for further videos, okay? Now in this lecture, I'm sure I say part and component at least many times. And it's because they mean the same, you know, but it depends on what industry you work. The parts and the components are the same thing, but sometimes people say component all the time or part all the time. And since I have worked in mechanical, aerospace, and civil quite a bit on all three disciplines, then my vocabulary gets messed up, and so to me, I could mention one or the other, all right? So, okay, so now, second is that we have to start to understand that the specimen and the part or component are not the same. The component will have less life than the specimen because the specimen is small, it's polished, it's subject to bending only, tested at room temperature. You see, all these restrictions will give us a life or a strength. And the component, no, the component may not be polished, maybe big, maybe it has shear or torsion, maybe high temperature, and all these things we're going to have to take into account. Now, the equations are valid for both specimen and component, but the parameters will have to be adjusted, okay? And so for now, how are you going to deal with that? The way we're going to deal is that anything that is a specimen, we're going to put a prime on it, which I didn't put in this lecture so that I don't complicate matters unnecessarily, but you see right there is the prime. So later on, when we see a prime, we say, this is a specimen, okay? But so far, since the equations are the same, I don't put the prime for now. So the HCF, which is the high cycle fatigue, all right, that's from NT to NE, is SF A N to the B, okay, we're done. This we learned. The LCF, which is low cycle fatigue line, is SF SUT N to the 6. We did this, done. I introduced the knockdown factor. The textbook doesn't call it knockdown factor, it just call it F, but that's what it is, I think. So the low cycle fatigue knockdown factor, because it reduces SUT down to that intersection, is F, which is defined this way, and we will find an equation to find this number exactly. We don't have to use a graph or anything, okay, done. And the slope C, we got this far, is log F. If we had F, or we assume F, we can calculate the slope and we're done like that. But obviously we have to do more because we don't have A and we don't have B, the intercept and the slope of the high cycle fatigue line, which we need in this equation right here. Okay, so all right, so next lecture will be a specimen fatigue. So we're going to work only with the specimen and work more with the equation so we can get more stuff out of it, both low and high cycle fatigue. Okay, the video, you know, for the student registering the class will be here, and when eventually the video makes it to YouTube, then it will be here. Homework, everybody knows where the homework is. And the app is not ready. I mean, It's ready but not validated, so I'm not releasing it. Okay, and so not releasing it yet. Okay. So I think that for that is for today is good. This is enough. All right. Thank you very much, and I'll see you soon.